So, look, thank you guys for having me here to talk today. I am here really to not only to talk about applications of Bayesian networks in the industrial sector, what we've been trying to do. So, I'm trying to bring forth some real world experience of trying to build models that can be used to help operators who are trying to make the paper that you guys use every day, and to make that experience one that you don't mind forgetting, or it won't be memorable in a bad way. Let's see if I can do this. Okay, so let me just tell you about my professional journey. I'm a mechanical engineer. I graduated from Washington University a long time ago, so I'm not even going to talk about the year. But I have been working in operations that entire time. So I've worked in production plants, maintenance, in terms of operations management. I've done engineering, equipment commercialization, and operations excellence and advanced analytics. You can see some of the companies that I've worked for down at the bottom. I've worked for Procter& and Gamble. I was making Cascade dishwashing detergent when it was still a powder, not those little things that you can recall. Uh, I worked for Coca-Cola where I did the bag-in-box bags that are actually part of the fountain equipment. I got 3 patents in that, working for them. I've also worked in what they call flexible film. So like all those packages you see on the store shelf where your food is packaged, and they have all those unique properties, so you can hold the freshness and keeping oxygen out and keeping things in. I worked for Crown Zellerbach, which then was taken over by James River. I did a stretch at ITW, making stretch films and commercializing specialized stretch film equipment. And that took me all over the world to Bulgaria and other places where we have facilities that were making equipment that made hand wrap. And then I have now been working for Coke and GP. Coke owns GP, right? As well as, you may not realize, Coke has a stake in Colonial Pipe as well. So, but I was doing advanced analytics, operations excellence, which really is just manufacturing 101. Basically going into mills, trying to teach them how to run their plants, and then working in wood products. Um, when I started with Bayesian networks, at least with Bayesian Lab, it was rough. I'm just going to tell you. Um, part of my problem was I started out with the generis, just like Kurt did, and you learn one set of some language, and now you're having to add in something new, some concepts that I'd never seen before. And so it was a little bit of a challenge trying to get through that learning curve, and trying to get around some of the prior knowledge. And then one of my strategies was to really get into this by building as many models as possible. At one point, I even mentioned to Lionel, I said, Lionel, it's not about the good models you make, it's about the bad ones. And I made a lot of bad models, starting out. But I learned from all of them. Also, what happened in GP over the last 4 years is they started putting a big emphasis on AI in operations. So they invested heavily in what they call Internet of Things. They're starting to do monitoring on their equipment to see if they can reduce downtime associated to equipment failures. And they also came up with this concept called operational settings. So what they could do was, if they could figure out in a process what these optimal settings would be, it was almost as if you could kind of set your equipment on these settings and it would almost run by itself. It was not what it was. It doesn't necessarily work that way, but I thought that it would be a good chance to apply Bayesian networks because, again, Bayesian networks being causally based might allow us to get some insights from these. We get some process insights, and we might identify some new opportunities in terms of how we run our equipment. And what I'm going to present to you today around toilet paper is just one of many different types of modeling work that I've done. I've done work in OSB, oriented strand board, on lumber kilns, gasifiers, where you're actually converting wood to syngas, where we actually built models for that. And then on plywood, where we're actually drying veneer. We're trying to figure out how we optimize the drying of veneer in our plywood plants. This helped a lot. And when you presented this years ago, when I first saw it, I struggled to understand it. But one of the things that really helped me to understand was the limits of machine learning and how you can apply it. I thought when GP launched this push into AI, there seemed to be a lot of hype. If you're not, I don't want to use the word hype, but it was as if AI could do almost anything, and it almost would allow you to leapfrog your manufacturing process. And I had to realize, I always kind of refer to this when I'm thinking about the kind of model that I'm building. And actually, it's very important to think about what is the purpose of your model? What are you trying to do with it? There's been many examples where I started out to build a predictive model, and then the customer comes back and says, well, can you optimize it? Why, yeah, but that's not the variables that I targeted. You wanted a predictive model. So then you're back starting all over again, having to redo your work and do some other things. The other thing I wanted to go back to on this, no, I'm going to keep on here. The other thing was, in my experience in manufacturing, it's really about process, procedures, and execution. And I used to have a boss. I don't know have you guys ever had the white glove boss who would come out, walk along in your department and do this, and then, walk along, and then he'd kind of get over here. And he was always pointing out to me, things that were right and wrong and what you should have been doing and what you should be doing. And the one thing I learned about manufacturing is if you follow the procedures and do what you're supposed to do, 99% of the time things are going to go okay. So, how much of this you really need is not, it's not that we don't need it, but if you look at what's happening in the world where manufacturing is going array, going in the wrong direction, it's a lot of it's because we're not doing the stuff that we're supposed to do. And he used to say to me all the time, this ain't rocket science. It's not. And I have to remember that every time I'm going out. When I go into a plant and look at it and I see it falling apart, I go, it's not that. It shouldn't be this. It should not be this way. So why tissue? Well, for GP, tissue is a huge piece of the business. It's a key revenue driver. Um, they're getting a lot of competition, especially from what they call non-integrated mills. Those are mills that don't produce their own pulp. Some paper mills, they actually make their own pulp and they also make the paper. But these non-integrated mills are actually becoming very competitive. And for a long time, GP had a very strong competitive position because most of their plants they were integrated pulp mills. Also, in terms of strategically, it was crucial to develop a model that we could use to help ensure customer satisfaction, that we're making products that were right. And you'll understand that better when you see how we test. And then the other thing was, when you're running tissue, sheet strength is important, not only to the end user, because you don't want tissue that's tearing while you're trying to use it, but it's also important because web breaks on a paper machine are the kiss of death. When a paper machine breaks the web, what they really don't do is they don't stop the machine. What they do is they actually just run it in a recirculation mode, and they capture the pulp in a tank. And then when they get it started up again, they start to feed that pulp that's already been through once back into the process. Because that's how it's very hard to it's very hard to rethread a paper machine once it goes down. You have to keep it going, recirculate it, and get it back in. So if you can keep the sheet strength up, you can be assured that you can get it from start to finish, and you're going to keep your process stable. And then again, the operational excellence piece, we were really trying to see if there's optimal production concept was something that we could actually discover something in it, and we'll talk about that as we get to the end about what we learned. So starting out, how do we start? We take logs, we transform it into wood chips. You drop them in a digester, you cook it in a caustic solution, which is going to break down the fiber. Then you're basically going to take those fibers, possibly, and you may run them through a bleaching process, clean them up, and then you're going to send them to a paper machine. And then you're going to start to form a sheet. That's the start of it. Digesters are huge. I mean, they're multi-story, hundreds of feet across sometimes, and they will cook for hours, maybe 12 hours to cook a batch. And then you'll empty it, and then you're filling up another digester, and you're cooking that. So you've got this constant process of going on. A paper machine making tissue can run sometimes between 200 and 300 tons a day. of tissue. Yeah, it's a lot of tissue being produced, lots of tissue. The other thing is, go back here. Once you get that pulp mixture made and you're getting ready to start the process, you're going to add things to prepare to actually enhance the paper strength so you can get it through the machine and so that you can also make the product the consumer can use. So they'll add starch in some cases to increase stiffness and bonding. They have what they call cationic starch that will also do that as well. And then they add wet strength agents that actually help the tissue to stay strong when it is wet. So you have these chemicals that are added just before you go into the papermaking process. And then the next step of the process, you have refining. So when you get pulp that comes from our digester, the pulp is a fiber, and these fibers are actually just long, they're strands, and they're all together like this. But what happens is what you're also is your pulp consists of hardwoods and softwoods. So what I mean by hardwoods are like eucalyptus, beech, hickory, mahogany. Those are maple, oak. Those are hardwoods. Those are short fibers. And what those fibers bring to the tissue is softness. That's where your softness comes from. 70% of the tissue is made from, typically today, it's going to be bleached eucalyptus, white eucalyptus. The other 30% is going to be softwoods. Those are going to be like your southern yellow pines. And you have your long fibers. But the issue is that they're still in a fiber, okay? And what you want to do is you want to break those fibers apart, right? And then you want to get them to touch each other, like form connections. These hydrogen bonds are what give you strength. The more of these you form, the stronger your sheet. However, there is a downside with all these bonds. As strength goes up, oops, I'm sorry. Let me go back. Or did I miss it? I'm sorry. Yeah, I missed a slide. As strength goes up, softness goes down. That's the way they work. So that's the thing you have to monitor in your process. And look, what happens is when strength goes up on a paper machine, the operators can run faster. So they can make more tons because the sheet's not going to break, right? So you have to think about that. And you're measured sometimes on tons in what you're trying to produce. So you want to make sure that you're not making a super strong sheet because you're also going to find out that it's not soft. And that will come back on you. This pulp mixture is basically pumped to what they call a head box, and it's just blown out onto what they call a forming fabric or a wire. And what happens is that when it hits that wire or that felt, it begins to drain. So the water drains out of it. So what you're doing is you're starting to form the sheet at this point. And it's very important to understand that the speed of the wire and the speed at which you're pushing it out can have an impact on the orientation of the fibers in the sheet. And what that will do is that will affect your strength directionally. You can have very good machine direction strength so you can pull it, but it won't have any cross direction strength. So when you take your finger, you can poke a hole right through it. And it's vice versa. You can get the cross direction strength the right way, but you don't have any machine direction strength, so then you get wet breaks. So you didn't realize all this was going on for your tissue, right? You're thinking, oh, it's just simply someone drops some stuff on a former, they run it through a machine, and bingo, we've got tissue. But there's quite a bit of science that goes into this. They call this rush drag. And that's really what you're doing here. And that starts the formation process. And again, this is also a process where you're trying to dewater this as well, get the moisture out. And I'll explain why here. This is called a Yankee dryer, okay? And I give you a sense of scale by seeing it sitting on a flatbed truck. It's about 18 feet in diameter. And this is where you form the softness in the sheet. It's hollow, as you can tell. It's going to be running at about 60 miles an hour. And it's going to be under steam, running steam. And this is where you're going to dry that pulp and start to make what they call the crepe that forms the softness in the sheet. And to give you a better picture of it here, so to start this process, if you look on the bottom of this picture, you'll see what they call an adhesive spray nozzle. So what you're doing is you're spraying a coating on the drum. And what that coating does is that you see the wet web coming from the left-hand side. So what happens is the wet web is going to transfer to the Yankee dryer drum, and the coating acts like an adhesive to pick it up. But it also acts like it helps with the heat transfer so that it dries out properly. And as it comes around the drum, so you're going with something that's 20% solids, coming in, then you're at 40% solids. You've got dryer hoods that are blowing air on it to dry it. And then you're coming around to the right-hand side, and you'll see on the right-hand side is what they call a doctor blade. And what that blade is doing is basically scraping the sheet off of the drum. But what you don't want is you don't want metal on metal contact. So what you're literally doing is you're scraping in the coating layer itself, literally splitting it. And the idea is when that blade hits that sheet, you notice that it's starting to make folds in it, and that's called creping, okay? So that drum is turning at about 5,000 feet per minute. At the end of the machine, the reel is running at 4,000 feet per minute. So there's 1,000 feet of material that's being creped. And what that crepe looks like is that's what it looks like. So what you have in your sheet is what they call micro creping, where there are these tiny little folds, and then you have these big fold overs in it, right? They call those macro crepes. That macro crepe, that's where your softness comes from. And you can measure these. So we have an instrument that we use called an MTech TSA softness analyzer. And what it does is essentially measures the macro crepe at 750 hertz, and it measures the micro crepe at 7,000 hertz. And it also measures the stiffness. It uses a proprietary algorithm to synthesize what we call a hand feel score, a measure of softness. So we use that. And you can see there's our King Kong size tissue roll that comes off the paper machine. That's the size of the roll coming off. That's weighing in tons. And the downside of all of this is that in most web-fed processes, even in plastics, where I work in the plastic industry, you get a roll off like that, you're going to take a few samples off the top of the roll, and basically, whatever those readings are, determine what that roll is. So, and if you're not doing every roll, which in some cases we're not testing every roll for softness, you can imagine that from test to test, you don't really know what the softness is, right? And that's a lot of footage. So what we were trying to do was basically use Bayesian networks to be able to identify those machine conditions that would allow us to predict what this tester would see. And then at the same time, that would allow the operator to be able to make adjustments based upon the measurements coming out of the Bayesian model. And so one of my early models is a very simple model here. Now I've anonymized it because I don't want to give away any secrets, but basically these are the features that are in that model. The felt and wire, what they call the life cycle, because again, what happens on the felt is over time, it builds up with pulp and you have to basically backwash it from time to time. And over a period of months, eventually you're going to have to replace it. And that's probably about $120,000 to $200,000 to change out a felt. You also have the recycled pulp that I talked about, that you want to measure how much you're putting in. You've got the head box dynamics. You've got a press section where you're squeezing the pulp before it goes to the Yankee dryer. You want to know what those pressures are, what those vacuums are, so that you can see what those are at. You've got the drying hood temperatures. You're also measuring the basis weight, which is essentially the density of the sheet. And then overall, you're looking at the sheet moisture management conditions. In other words, how dry is the sheet as it's coming off the Yankee dryer? If the sheet is not sufficiently dry, you will lose crepe and you'll lose softness. And there's winder and calendar and operations, et cetera. So the red tags in this model are basically variables that we're controlling. And then the green tags we identified as non-confounders in the process. So my first model that I built here was a very I have to say it was good in the sense that the mill that produced this product was a very well-controlled mill. They were also an integrated mill, so they made their own pulp. And the model was strictly for prediction. But that's what it came out to be. And what some of the things that we learned from it were, so if you look at the model performance, one of the ways that we did our learning and test sets were that because this is time-based, what we did was we would learn our learning set was basically at earlier roles, like we would get collect data over a period of months. So let's say we would look at roles that were made from January through March, and then our test data would be on the data that came afterwards. And so really our first models were very small because it takes to generate a role takes about 45 minutes, and you're only testing like 1 in every 3. So to get 1,000 roles of data could take months. So this is another reason why we use Bayesian networks, because it's really good for small data sets. And so in order to be able to use this, I used the model and reparameterized it as I got more data so that we could, and then when you guys came up with the Python export, we were able to generate that code, and then we end up putting it on a monitor in the operator's control room. It ran for 2 years. In fact, I didn't even know it was still running, but it was still running. So it was helpful for these guys, but again, they were very good operators to begin with. So but it was a way for them to be able to get a TSA value while the role was building, and to be able to look for trends. If something was starting to go low, then they could make adjustments to bring it up. Also, with the direct effects analysis, total effects analysis, if you identified the right factors and non-confounders, what we found was that they were consistent with papermaking knowledge. So if you run the machine faster, softness goes down. If you run the web wetter, softness goes down. Let's see. If you run the basis weight higher, put more material in the sheet, the softness goes up. So all that was verified by what we were able to put in our initial models. The only thing I had challenge with, and I'm just going to bring this up, this is something I learned more recently, was, we were trying to figure out whether we use K-Fold cross-validation, which it performed poorly on, or Jackknife. And I just bring this up because I have come to love ChatGPT, because I could simply go in and ask a question. Sometimes when I can't reach Stefan, he's busy on the phone. So I asked ChatGPT which was the best method for evaluating this. And I get this nice long paper, and it kind of gives me a little bit of feeling that it's not so bad, that what I'm doing is not too far afield. So I consider that my a little hindsight, and thank you for ChatGPT for allowing that for coming into existence. And now that you've tied Alexia to that, and I have my own ChatGPT account, it works really well. So I can recommend you, if you have a question you're struggling with, you can certainly frame it up for ChatGPT and get a relatively good answer. So we came across another problem with softness on another paper machine. And so we got 2 tasks. We had to develop a predictive model, and then we were trying to figure out how to identify and apply adjustments to bring it back in control. They were having problems getting tissue softness. And I'll show you what it looked like here. So again, the data is anonymized. The x-axis is time, and the y-axis are our hand fill readings. And what the data show was 2 clusters. So the red cluster is stuff that's primarily in spec. We were performing well. But the green data shows that sometime in this time period, it's like the tires fell off the car. I mean, this is like months. And we couldn't figure out what was going on. And so all the readings were coming out lower. And they wanted to sit down and see if we could figure it out. Now, there are some things that they were assuming about that, we could build a model, and there were certain things that we didn't need to consider, and that we could come up with an optimal set of conditions that could move this green into the red. And I'll talk about that too. But the problem is that, one, we have a shift in the process. The current data that you're looking at on the right-hand side doesn't show any in-spec performance. We're trying to capture all this with the existing, what we call tags. In other words, we're pulling data out of our historian to tell us what the process is, those tags. And then we're making some assumptions about external factors like seasonality and some of the internal factors about raw materials. They were not influencing. I think that was something that probably was not true. And then we had a number of mill interventions that forced us to filter out some data. You can see some gaps in here. We would build a model and then we would test it and it wouldn't work. And then we would come back and find out, oh, something was broke. We swapped out some tags. We had to do this. So you need to take that data out. Start over, build another model, test it again. And so we had several times when that happened during the process. And that's some of the challenges, which is just in working in an industrial environment. Remember, they're trying to make production. They're not about, this is not a design of experiments. They still have orders they need to produce. So that's one of the challenges you have. We even had calibration issues with the TSA machine. So again, these are some of the challenges that we had to deal with when we were building this model for this particular problem. This is the model that we generated, that we came up with. It essentially has the same features that you saw in the first model, pretty much exactly the same. The challenge with paper machines in our company is no two are alike. It's not like we standardize. So every model you build has different, they may have some equipment, they may not. They may pipe it this way, they may not pipe it that way. They may have other things that are different. So every model is not necessarily going to have all of these in it. And generally they'll have most of these, but they will be different for every machine. So basically we came out the same way. Our direct effects and total effects analysis was consistent with the papermaking knowledge that we had before, which was good. Our model performance was okay. But one of the things I learned about this, and I come back and it really made me ponder was, again, this is not design of experiments. So we weren't doing any multi-factor type of data analysis or setting that up. I call this MBE, man's best practices, or man's best expertise. That's all you're putting in. You're not putting in data. So basically, you're getting whatever the operators are able to do, which is going to be limited, which is going to be affected by their skill set, their biases, what they know. And that's going to put a limitation on the data that you're putting into the model to begin with. And then you're supposed to optimize off of that. And that's a problem. So this is the actual learning and test set. So the hand fill values are in blue. What Bayesian lab predicted is in orange. So this is expected value, that what you're going to get from Bayesian lab. The good thing was it tended to follow the trends, and even the test data wasn't as bad. But we always had a challenge with the test data. And I think that's partly because of either the seasonality issues. In other words, you almost need a year's worth of data or go through the entire seasons. And we were always challenged to get that data. And then we had some challenges collecting some data because of issues with the machine or with our equipment. But going forward, we pushed forward, and we did the greedy and genetic search algorithms and came up with recommended operate optimal conditions. And they looked fine. But I'm going to tell you something. Those optimal conditions were contained in man's best effort. In other words, the question you ask yourself is, if those optimal conditions were contained in the data that we already had, why weren't we running it? And the reason we probably weren't running it is probably because we had some latent factors that were missing, or we had some things that we had not identified in the model, and some of the assumptions about how we were supposed to come up with this were not correct, like that you didn't need to consider the pulp that was going into the machine, because that's not important. And that was some of the thinking that was going on in our business, that we were buying pulp on price, you know, and making the assumption that, well, it didn't matter, it shouldn't affect us that much. But what this began to, what to begin to do is begin to unravel and show that we had some factors in there that we needed to start looking at more carefully. And then again, when you're trying to assess a Bayesian network model, when you're trying to look at the considerations that could explain why these recommendations weren't being employed, we got data integrity, we have adaptability, comprehensiveness, the human element, model, complexity, verification, and communication. These are, I'm not going to go into detail on each one of these, but these are the things you want to start looking at. But I kind of had an idea what part of the problem was. So the project stopped, some months went by, and then an opportunity came up where we could revisit this in a different way. Our procurement team wanted to start looking at what they were buying. And what I was able to do with the data was I was able to enhance it with a little more information. And I was able to add to it the particular pulps that we were running. So what happens in a paper plant, our paper plants, is to secure the supply of fiber to the plant, you usually have two sources of eucalyptus and you have two sources of softwood. So what does that give you? Four combinations. And the plants they just grab stuff and run it. In other words, they'll grab some of this and mix it with this. They'll grab some of this, mix it with this, grab some of this. They really don't have a very good process for how they blend, how they choose, and how they run. So what you had to do is go back and look at this a little differently. So with Stefan's help, I started looking at trying to build a model where we could look at a number of things simultaneously. So I wanted to look at softness, and I also wanted to look at machine performance, and I also wanted to look at some of the quality metrics that were coming off the machine. And then I wanted to weight them. And then I wanted to do an optimization, a function optimization using a weighting. So that what happens, I said, look, softness and runnability are our two key factors. They're the top two, so they're weighted the same. Some of these other things like MD stretch, which is a ratio of the stretch ratio between machine direction and cross direction, CD strength, and those are things that are not as important. But I wanted to optimize, build a model that would allow us to see if we could see what's the best we could do with each of the different pulp combinations that we had. And so we have the pulp in here now. We've identified it. We have a model that we're looking at trying to maximize the performance across a number of features, and we're doing function optimization, a scoring system. And what it ultimately revealed was that for the most part, operators were doing the best they could with what they had. The real issue was you got to change the way you're buying fiber. You can't just look at fiber as something as a price issue, because these different combinations, they're like kids. Sometimes they don't play well together, and they can affect your process. And so instead of buying 50% mix of BEK, right, two of the same, you might want to unbalance it and buy a larger factor, a larger percentage of one that works really well and a smaller percentage of the other one, so that you can minimize the amount of time your machine is running a combination that's not good for it, that doesn't run as well. That was one of the things we wanted to see. The other thing was, if we were going to improve the analysis going forward, we started to need to include fiber characteristics and machinery and mill specific factors. And then the other thing that also came up with this was, and something your Alexia couldn't have come along at a better time. We wanted to sit down and start trying to understand what fiber properties were primarily responsible for affecting the quality and performance on the machine. And they run all kinds of tests on fiber length, they call it kinks. They have other properties that they're measuring. And so we need to sit down and figure out which one of these, what we want to measure and what data we can get so that we can understand how these properties are affecting the outcomes on the machine. And then finally, this kind of leads to a strategic approach called total cost of ownership. Because what's happening is if you're buying something for $500 a ton, but then it's costing you another 100, it's actually costing you $600 a ton. And so what we started to do, we started to look at building models to where we could calculate a total cost of ownership with these combinations, because we couldn't separate them. We can't say that the softwood is this and this. It's always some combination. But if we could start looking at it that way, then we would understand what the true cost of the fiber is. And then that gave our procurement group the ability to go out and negotiate and try to get better prices, or to try to rebalance what they were buying for a specific mill. And the broader learnings I got from this is, I love this data science stuff. I mean, I think it's great, but it doesn't replace operations excellence principles. You still have to follow the rules. And one of the things that they did was they kind of went overboard on the data science side, and actually they canned the entire operations excellence group, which I thought was really not the best idea, but we did that because I guess people kind of sometimes think that if I do this AI, I can somehow leapfrog over all my bad habits. And you can't leapfrog over bad habits with AI. You still have to follow the rules. And that's the key thing. The other thing is, with all of this AI and these data analytics and so forth, you've got to assess people's readiness for it. When you start monitoring the machine with all of these and running a model, that means you have to go out and maintain those components. You have to go out and make sure they're calibrated. You have to go make sure that they're maintained. If something is not working, your model stops working. Okay? And in some cases, even when operations excellence, when we went into mills trying to teach them how to do manufacturing 101, we would do a readiness assessment to make sure that they had the right culture, they had the right people, they were kind of already aligned, they were ready, they had a readiness to accept what we were going to explain and how they were going to have to change. Well, if you're not there, putting a model is a waste of time. So if you're not committed to model discipline, maintenance, support, don't waste your time doing it. And then there's aligning the goals with the customer expectations for the synergistic outcomes. Questions? Yes.